We're going to talk about energy transfer mechanisms in thermal processes, and these are basically thermal conduction, convection, and radiation. So the first one I would like to address is thermal conduction. In thermal conduction we have heat transfer. So basically when we make a thermal contact between two objects, it's the process of energy transfer by heat across the boundary of a thermal contact is called thermal conduction. So it is the process of energy transfer by heat. Okay, so once again, this is going to happen if we have a thermal contact. And on the microscopic scale, when we zoom into this boundary, we realize that what exactly is going on is we have an exchange of kinetic energy. So we have the process going on the microscopic scale, exchange of kinetic energy between microscopic particles. This can be atoms and molecules of a solid, it can be gas particles, etc. And if we look at a substance here, a sample, and we have connected one side of the sample to a hot energy reservoir, so this boundary is kept hot and one side is kept cold, so this boundary is kept cold. And if this sample has a surface area A, so we take basically a slab here, so this has surface area A, so that's going to be the cross-sectional area here, and the temperature on one side is TH, that's the hot side. The temperature on the cold side is TC, and we know that heat must flow from the hot side to the cold side, because in order to reach thermal equilibrium we have to have flow from the hot to the cold side. And I see that this slab has a thickness delta X. In that case, the rate of heat transfer, the rate of energy transfer by heat, the rate of heat transfer, that's basically energy flow rate. It's going to be power, but that is equal to dq dt, is going to be proportional to the cross-sectional area A and also the gradient of temperature, delta T over delta X. So this takes us to the law of thermal conduction. Basically, the law of thermal conduction states that the proportionality constant here is called thermal conductivity. The power, the rate of heat flow, is kappa times the cross-sectional area A times the absolute value dt dx. Now, why do I need an absolute value here? There is another way to write this equation. Basically, I can define heat flux. Heat flux is the flow of heat flux per area. So that's going to be Q per area per unit time. So that's this funny Q. It is minus kappa dt dx. So basically this heat flux per unit time is 1 over area dq dt. And why do I need this minus sign? Because this kappa, the thermal conductivity, is defined as a positive number. It depends on the material. And in order to have a positive thermal conductivity, you can notice here that this is your x-axis, and the temperature is decreasing as we go along x. So for a given positive delta x, I have a negative delta t, and therefore I need to introduce this minus sign so that I get kappa, the thermal conductivity, to be positive. And what is the unit of kappa? So we can use either of these equations. Basically, I will concentrate on the power here. Well, the unit of power is watts, so it's going to be watts per meter Kelvin. So that's the unit of power, because I have meters square in the area, so that turns into meters. So watts per meter Kelvin, or it can be given as watts per meter degrees Celsius, one of the other. So that's the situation when we have a single material that is sandwiched in between two energy reservoirs, a hot reservoir and a cold reservoir, so that these two sides are kept at constant temperatures. There is a continuous flow of heat, and this heat, I have to distinguish between heat and flux here. So this is Q, the heat flow. All right, and for this case, the power, the rate of energy flow is kappa times area absolute value of dt dx. Now there is an interesting situation when you have two materials in contact, but before we get into that, let's note here that the thermal conductivity is pretty high for metals. So for some substances we have very good thermal conduction. Metals such as gold, copper, silver, etc. These are good thermal conductors, so they have a high thermal conductivity. And on the other hand, gases in general, insulators such as silicon dioxide, for example, glass, are poor thermal conductors. Okay, so let's look at the situation where we have two materials in contact with each other, two slabs of thicknesses L1 and L2. Thermal conductivities K1 and K2 are in thermal contact with each other as shown in the figure. The temperatures of their outer surfaces are Tc and Th, where Tc is less than Th. So H stands for hot, C stands for cold. Determine the temperature at the interface, and the rate of energy transfer by conduction through an area A of the slabs in steady state condition. Okay, so if I concentrate on this problem, I see one side is hot, so this is the hot side. There's the temperature TH here. One side is cold. There is the temperature Tc here. And then I have an intermediate boundary. So let's show that with green. So this boundary is going to have a temperature that is in between Th and Tc. I call this T intermediate. All right. and the lengths of the two slabs are L1 and L2, and thermal conductivities K1 and K2. So I already know the law of thermal conduction for one material. So this is basically the law of thermal conduction that is for one material. Power is equal to kappa times area dt dx. And if I apply this law to material 2, the power, the rate of heat flow, should be K2, its cross-sectional area A, multiplied by dt dx, delta t over delta x in absolute value. So what do we mean by x? This is the x-axis. All right, so this is going to be equal to K2 times area A, the absolute value. So I have the following relationship between temperatures here. TH must be greater than T intermediate, must be greater than TC, so that I have heat flow from the hot side to the cold side. So this is going to be in absolute value, so this will be TH minus T intermediate divided by the distance L2. And at steady state, the rate of energy flow from the left to the right must be the same across both samples. So this must be equal to also K1 times A for the second slab. Now the heat flows from T intermediate to TC. So this is the hot side for the second sample. This is the cold side, and this heat is flowing through a distance L1. So I see that these areas cancel, and if I multiply both sides with L1, L2, so I want to multiply it by L1, L2, basically what I will get is K2 L1 T hot minus T intermediate is equal to K1 L2 T intermediate minus T cold. Alright, so I'm trying to solve for the temperature at the interface, so T intermediate. So how can I solve for this? I have to isolate it. So K2 L1 T hot minus K2 L1 T intermediate is equal to K1 L2 T intermediate minus K1 L2 T cold. So if I take this T cold to the left hand side, I will get K2 L1 T hot plus K1 L2 T cold is equal to K1 L2 plus K2 L1 T intermediate. So basically I can solve for the intermediate temperature. It's going to be equal to K2 L1 T hot plus K1 L2 T cold divided by K2 L1 plus K1 L2. So this will be the intermediate temperature at the interface between the two samples. The second question is, what is the rate of energy transfer by conduction? So I can substitute this result to one of the power expressions. So let me separate these two parts. Now I can substitute it into the power. The power is equal to K2 over L2 T hot minus T intermediate. So it's going to be minus K2 L1 T hot plus K1 L2 T cold divided by K2 L1 plus K1 L2. So I have substituted this result here. And this is going to give me power is equal to K2 over L2. So the first term is T hot K2 L1, so that will disappear. I will have K1 L2 T hot minus K1 L2 T cold divided by K1 L2 plus K2 L1. So if I operate this with L2, so this is what I will get. The power is equal to K1, K2. Of course, I have the area in the power expression too, so I shouldn't forget that. There is the area. So K1, K2, T hot minus T cold times the area divided by K1 L2 plus K2 L1. So what I'm going to do is divide the top and bottom with K1 K2. So I will find that the power is then area times T hot minus T cold divided by L1 over K1 plus L2 over K2. So this is the final answer for the power at steady state. The rate of steady state means the rate of energy flow is a constant across this interface. Both from the left side and the right side, it's the same rate of energy flow. Actually, this result can be generalized to n materials that are in thermal contact. So we will see that in general for more than one material, for n materials in thermal contact, we can write the following. The power is equal to area T hot minus T cold divided by sum over I, goes from 1 to n, and different materials, their lengths Li divided by their thermal conductivities kappa I. That's the generalized law of thermal conduction for many materials. And because this ratio length divided by kappa is very important, and we need to add this quantity to find the total value that we have to put at the denominator, L over kappa is called the R value. R is like resistance. So when you have resistors in series, you add their resistances to get the equivalent resistance. And this is when you have so many thermal conductors in series, you add their R values to get the equivalent R value. So that is sum over I, Li over kappa I for the ith thermal conductor, for the ith material. Okay, so there's another way of transferring energy. That's called convection. And what is convection? Convection is the transfer of energy by the motion of a warm substance. Okay, so transfer of energy by the motion of a warm substance. And here is the example you can see here. at your home you have a radiator, and this radiator basically heats up the air on that's close to the radiator, and this warm air rises and basically cycles through your house, and it's the motion of this warm air that's around the radiator that is causing the transfer of energy into the whole room, and therefore it's energy transfer by convection. Now there are two types of this we can talk about. We can have the so-called natural convection, or we can have forced convection. There is the natural version and there is the forced version. So basically what I have described here, you have this radiator, the warm air molecules moving around. For example, this is driven by the change in the density of air molecules, of air. That's going to be a natural convection. On the other hand, if you put a pump or fan here, so if I introduce a fan, so I put a fan right next to this guy, so this fan will be rotating, and let's say that it sits here, it's rotating like this, it's going to blow the warm air into the room, right? So that will be, so this is a fan. So if you have the fan here, then you have the convection driven by a pump or a fan. That will give you a forced convection. So the air molecules are flowing inside the house. They are forced to move by as driven by a pump or a fan. There is the third type of energy transfer. It's by radiation. And what is the driving force for this? Well, all objects at a finite temperature will radiate energy in the form of electromagnetic waves, and that's due to the thermal vibrations of the molecules. When you take a class on electricity and magnetism, you will see that electromagnetic waves are generated by accelerating charged particles, and that's what you have in all objects because of the thermal vibrations of the molecules, and therefore all objects radiate electromagnetic waves. All right, so that's the first point here. All objects radiate energy in the form of electromagnetic waves, and that is due to thermal vibrations of atoms and molecules. How much is the power radiated by an object? That's the answer is given by Stefan's law. Stefan's law states that the radiated power from an object is proportional to the fourth power of its temperature. The proportionality constant is Stefan's constant sigma. It also depends on the cross-sectional area, the emissivity, which defines the ratio of emitted to absorbed radiation, times T to 4. So this sigma is Stefan's constant. It has a value 5.6696 times 10 to minus 8 watts per meter square Kelvin to the fourth power. A is surface area. T is surface temperature. So that will be in Kelvin. And E is emissivity. Emissivity. It's the ratio of absorbed radiation to incident radiation. So when you have electromagnetic waves hitting a surface, part of the electromagnetic waves may be absorbed, part of the electromagnetic waves may be reflected off the surface. And if you have an ideal absorber of electromagnetic waves is called a black body, and it has an emissivity equal to 1, which means it's going to absorb all the electromagnetic waves that is incident on the surface of the object. Now, let's say that we have an object at a temperature T. So if an object is at temperature T and the ambient temperature that's the temperature of everything else is T0. Then what is the net power radiated by this object? Assuming that T is greater than T0, the object is hot compared to its environment, there will be net power radiated by this object. It is given by sigma A emissivity T to the 4th power minus the ambient temperature to the 4th power. So the power radiated is given by Stefan's law, and the net power radiated depends on the temperature of the ambient temperature and is given by also Stefan's law, taking into account the radiation of the object and the radiation coming from the environment.